for this opportunity. It's really great to have Chirality conference at home. So this is I really appreciate it. And I would like to summarize in this few minutes what we are doing at the University of Vigo in the chemistry with a twist team. We combine this design and synthesis of chiroptical robot systems, go on the understanding of the chiroptical mechanisms, and go for some applications. And we are moving around between them so that we are gaining understanding on the game between all of them. To start with, this is something that most of the audience in the Chirality conference are familiar with, the excitant coupling. Wherever we have two chromophores interacting with each other in the close vicinity, there come these non-degenerated two states that depend the distance between them, the energy gap between them is depending on this excitant coupling, this Davidoff splitting. And whenever the arrangement between these two chromophores is chiral, then you get one positive and one negative rotatory strength. So you will get your CD signal. Now the issue here is whenever these two transition states are very close to each other, there is a mutual cancellation between the positive and negative CD band, and therefore you pretty much get no CD. So a way to improve the CD signal is do some engineering that you can pull apart these two transitions from exciton coupling, and therefore you reduce the mutual cancellation between them and you enhance the G factor. So based on this, and this is the main driving force of the research we are doing, it's based on exciton chirality. So we use chiral access where the connectivity between the two branches of the individual moieties are not conjugated. These spiral bifluorines, Nazario Mati was mentioning in his talk that there is no communication pretty much between them. And we were tuning the properties of these systems by functionalization with cellulose, vinyl systems, even metal aromatic systems or tetracyanobutadienes, and even functionalization to anchor them to surfaces and be able to do some device-compatible chiroptical systems. Just to give an example of a specific one of these studies, Ivan, who had a poster yesterday, was using diformyl spirobifluorines and functionalizing them through covenant condensation to modulate the extent of the transition electric dipole moment of the interacting chromophores, and in this way the small increase or one-fold increase on the transition electric dipole moment was pushing 5 times the G factor up. So this is a kind of an experimental combined theoretical proof of this methodology. Another way to push these two vectors, these two transition opposite rotatory strengths apart, is by moving from dimeric to trimeric to tetrameric. So you start including in your system the number of chromophores that are arranged in a symmetric way to keep in the, not to start splitting many transitions, and you will get also just 2 transitions, one positive, one negative, but on the way that you are incorporating new chromophores, you are pulling apart this, and therefore increasing the chiroptical responses. Because of that, then we were also using this moiety with this diacetylene spirobifluorine, where you have the 2 independent chromophores. Whenever you do this dimeric system, then it becomes like 2 plus 2 chromophores in the end become another 2 chromophores. They merge through the conjugation of the acetylene, or whenever you get 3 systems, you can imagine that there is 3 interacting chromophores or 4 interacting chromophores. To understand that these are systems that are excitonic, this can be a very simplified picture, and we have really for a long time already having a extremely satisfactory collaboration with Fabrizio Santoro from PISA. He is the world leader about the prediction of systems whenever there is vibronic coupling, and this is the case of our system. So it's quite tricky to understand that. They have developed the FC class model, so they can really do all these calculations, and they know how to do this. So it's really a pleasure, and it helps us to really understand and to know that what our approximations are actually kind of not so far off the trail. So, going to the application part, we had a couple of talks, at least one from Luis Alvarez de Cienfuegos and another yesterday from Magali, which were focusing already as to introducing to us the cis effect, and particularly Magali yesterday was talking about the oxygen-evolution reaction, right? It's a reaction that is not chiral, but where chirality can play a role. And due to cis, so you have the cis effect, you can filter through the spin of electrons, and then you more easily come to the oxygen part, that is the ground state of oxygen. So what we did is we tried to test our systems into that also, the spiroeffluents, because they are pretty stable. We really understand the system. Often the systems that have been employed until now are not really deeply understood on the mechanistics, and this is something still missing on the field, and we thought we can contribute on the way to that. And so we just simply deposit by drop casting into nickel electrodes and perform the oxygen evolution reaction, and this is the work that Julia was presenting in her poster also yesterday. And we saw that whenever you have the systems with a higher G factor, there's a considerable increase of the performance of one of the enantiomers and not the other. And whenever there is the monomer with one order of magnitude smaller G factor, then there is no much effect. So we were curious about this, like you have a difference between enantiomers. There are not so many cases, but there are some cases about this. And when often we hear about the definition of chirality, we just think of these two mirror images that are not superimposable to each other. But when we think about electronic transitions, then we need to see that whenever you have a transition electric dipole moment, there is an associated transition magnetic dipole moment for one of the enantiomers, and for the other enantiomer it has a different angle. They are supplementary angles because one of the vectors is axial and the other is polar. So not only one of them is inverted to the center. So our observation through these examples is that when you look at this enantiomer that has the better performance, you look at the lowest electronic transition, CD band is positive, and this is the case for the two examples we have. So, okay, but this is just two examples. If you look at the case Magali was mentioning also yesterday, she did not refer to the enantiomeric differences, but they also observed for the helicins on surfaces that the helicin showing this positive CD band was the one performing better. And even Isabel Pastoriza, they had some examples of these nanoscience peroxidized, even with magnetic field or without magnetic field, always the system that was performing the positive band was the one performing better. We don't know why. This is an observation, and this is something we want to go into. There is just a very recent paper from Naman and Peltier and others, where they now focus on cis differences in absolute values between opposite enantiomers. Until now, many of the examples they were mentioning, this is just a matter of the device, building of the device, and you cannot really see that there are differences. Now they are pointing that there is probably, or they point to this angular momentum redirecting within the frame of the molecule as a possibility in handedness differentiation of the dimension of the spin polarization. So that's something we want to look into that in the coming time. So hopefully for next meeting I can tell you a little bit about this. And what I wanted to actually talk mostly today about is something also trying to open new spots about the impact of chirality that typically people don't look at them. I've been interacting the last year with David Andrews, and we were looking at resonance energy transfer. What is can chirality have an impact in resonance energy transfer? In resonance energy transfer, we have just an excitation from the ground to excited state of a donor, and then there is a energy transfer, so the donor gets relaxed and the acceptor gets excited. Typically, this is understood and in a very good way and being extremely useful through the Foster theory. And Foster theory considers the system, the understanding of this as the electric dipole coupling. So this is blind to chirality because here there there is no transition magnetic dipole moment. Now, when we consider that, just for simplification, we consider only donor is chiral and the acceptor is achiral, we could have two possibilities concerning the handness of the enantiomer. Parallel or anti-parallel transition electric and transition magnetic dipole moment. And now, because we take these terms into account, we cannot just consider the electric-electric interaction, but we also need to consider the electric-magnetic and magnetic-magnetic interaction. I will not get too much into detail here for also time reasons, but the term that is actually having a differentiation between the two enantiomers is the electric-magnetic term. And if you do the rate between the difference between the two enantiomers of the donor respect to the maximum rate, you see that depending on the chirality of the donor and the relative orientation between donor and acceptor, there are differences on transfer rate. So there is an effect. Is this applicable for any case? We don't know yet, because whenever you mirror everything, you get the same, right? If you mirror everything, you go from this enantiomer to the opposite enantiomer of the donor and to the opposite relative orientation between donor and acceptor, you get exactly the same way. So principally, you could not see differentiation between enantiomers unless you really fix donor and acceptor. Another thing is what can come after that. If you have an absorption, then the transition, the resonance energy transfer, then the acceptor can also emit light. What typically people think is like, or how is it treated? This acceptor is achiral, so it just emits achiral light, unpolarized light. Now, what we propose now is that if this acceptor goes through scattering and there is the emission of this light through the scattering of the donor, then this donor can imprint chirality there, and that's what the imprinting can come on it. So that's something we are now discussing, and from this you can decouple the primeness and the handedness of the donor and acceptor, so this can be quite useful for future applications. So with this, I just wanted to get this quick look at what we are doing, and I would really like to thank the team. It's really nice being at home and having the conference, the Chirality conference meeting here. We had a really nice representation of the team here. I would like to thank all the collaborators and funding agencies and the organizers. One thing I really like from this conference, I would like to take it for our next conference that I participate in the organization, is like this team therapy that we had yesterday after the gala dinner. Thank you very much for your attention.